Imagine hitting, 1.5 million messages a second.
Right, with a median published latency of like 3.88 milliseconds.
Yeah. And absolutely zero failures over a sustained stress test. And doing all of that on just 3 bare metal servers.
And running the CPUs at only about 70% capacity.
Exactly. I mean, it sounds like a totally hypothetical, white paper scenario.
It really does.
But it's actually a documented benchmark.
Yeah.
And when you start looking at the actual mechanics of how a system achieves that kind of throughput while maintaining strict order and durability, you realize this isn't just about, moving data faster.
No, not at all. It's about rethinking the entire data infrastructure stack.
Right. Because today our deep dive is pulling apart Apache Pulsar. And our mission here isn't just to review yet another messaging platform. We are looking at a system that handles high-throughput event streaming, traditional message queuing, serverless computation, and infinite tiered storage all at the same time. So by the end of this deep dive, we really have to ask ourselves, if a platform can do all of that natively, are we witnessing the beginning of the end for the traditional database?
It's a pretty bold premise, but, the architecture totally supports the argument.
Yeah.
To understand why, we really have to look at where Pulsar came from.
Right.
Yahoo originally built this entirely out of necessity. They had this globally distributed organization, massive multi-tenancy requirements, and just a scale that was totally breaking their existing infrastructure.
Yeah.
They needed a unified fabric that didn't just degrade every single time they added a new team or a new cluster.
Right. And the fatal flaw with those older systems they were running was just how tightly coupled the architecture was. Like if you look at traditional setups, the broker receiving and routing the data, and the storage, the actual disk writing the logs, they are physically bound to the exact same node.
Which creates just a massive operational bottleneck. If you run out of disk space, you have to buy a whole new server that includes CPU and memory you don't even need. Or, if you need more processing power to handle a spike in connections, you're forced to buy more storage just to get the compute. It's incredibly inefficient.
So Pulsar just severs that tie completely. It splits the architecture into stateless brokers for compute and Apache BookKeeper for the durable storage layer.
Exactly.
So the brokers handle the routing, but they hold zero persistent state. They just pass the data down to the storage nodes, which they call them bookies, right?
Yep, bookies.
And then you have Apache Zookeeper sitting on top of the whole thing, just managing the metadata.
Right. And that separation, that's the mechanical advantage of the entire system.
Yeah.
Because the brokers are entirely stateless, they can be scaled up or down instantly.
It's kind of like a massively over-engineered restaurant.
Oh, I like that.
Yeah, so traditional monolithic systems, they're food trucks. The cashier taking orders and the kitchen cooking the food are literally crammed into one single metal box. You get a massive Friday night rush. You can't just add more cashiers. I mean, there's no physical room. If you want to scale, you have to buy an entirely new, fully equipped food truck.
Right. But Pulsar separates the front of house from the back of house.
Exactly.
The waitstaff taking the orders, those are the brokers, and they are completely decoupled from the kitchen, storing and prepping the food, which is BookKeeper.
Yeah.
So if you have a sudden influx of client connections, you just spin up more brokers.
Yeah.
You don't have to touch the storage layer at all. Or on the flip side, if you suddenly need to retain, petabytes of historical data, you just expand BookKeeper without spinning up idle compute instances.
That makes total sense for resource efficiency. But, efficiency doesn't mean much if the application layer can't actually do what the developers need it to do.
True.
And this is where I kind of want to get into the actual messaging paradigms, because right now, most engineering teams are running a dual stack.
Oh, yeah. Always.
You've got Kafka handling the high throughput, replayable event streaming. And then you have something like RabbitMQ or ActiveMQ handling the complex point-to-point worker queues. But Pulsar claims to unify both of those.
It does. It actually bridges the gap between those two fundamentally different paradigms, totally natively.
Okay, but I have to push back here because mechanically, those two paradigms are completely at odds with each other.
They are.
Kafka gets its massive throughput specifically because it doesn't track individual message acknowledgements per consumer. It just tracks like a single offset for a whole consumer group.
Right.
So if Pulsar is doing shared queuing where, consumer A processes message 1, consumer B processes message 2, and C gets 3, the broker has to track the acknowledgement state of every single individual message.
Yeah.
At millions of messages a second, wouldn't that metadata overhead just completely choke the system?
Well, that is the exact trade-off that plagues other platforms, right?
Yeah.
But Pulsar handles it by utilizing how BookKeeper manages cursors. So instead of the broker keeping all that granular state in its own memory or, locking a database row, the acknowledgement state, the cursor, is actually stored as a continuous stream of ledger updates in BookKeeper itself.
Oh, wait. So the acknowledgments are just treated as another data stream.
Exactly. The brokers batch those individual acts and write them asynchronously to BookKeeper. So you get the granular message-level tracking required for traditional queuing without those massive synchronous locking penalties that usually, bring high-throughput systems to their knees.
That perfectly explains the mechanics of how it actually survives the load.
Right.
Which I guess is what allows Pulsar to offer what they call flexible subscriptions.
Yes.
You essentially just tell the broker how you want the data delivered. Like if you want strict Kafka-style streaming, use an exclusive subscription. One consumer gets the whole ordered partition.
Right. And then if you want the RabbitMQ-style worker queue, you use a shared subscription.
Yeah.
The broker distributes messages round-robin to a pool of consumers. And if a consumer dies, any unacknowledged messages are just instantly reassigned to someone else.
Okay. Then you have failover, where standby consumers just sit idle, ready to take over the primary stream instantly if the active consumer drops.
Right.
But the one that really caught my eye in the sources is key shared.
Oh, key shared is incredibly elegant.
Yeah.
In a purely shared subscription, you lose ordering because messages are sprayed randomly across consumers.
Right, of course.
But with key shared, the producer assigns a key to the message, say a specific user ID or a transaction ID. The broker then guarantees that all messages with that specific key will always be routed to the exact same consumer in the pool.
Oh, wow. So you get the horizontal scaling of a worker queue, but you maintain strict chronological order for specific subsets of data.
Exactly.
You aren't forcing a single consumer to process the entire fire hose just to keep one user's transactions in order.
Precisely. And remember the Yahoo origin story. They built this for an organization with hundreds of teams.
Yeah.
Kafka historically struggles with strict multi-tenancy. Teams end up stepping on each other's toes, so companies just spin up totally separate physical clusters for different departments.
Which creates massive operational sprawl.
Huge sprawl. But Pulsar has hard multi-tenancy baked into the architecture from day one.
Wait, so it's not just logical namespaces?
No, it's both. So at the top level, you have a tenant, say the billing department. And inside that tenant, you have namespaces, like development, staging, and production.
Okay.
You can apply strict I/O quotas, authentication, and storage policies at any of those levels. The network and storage layers enforce this isolation dynamically.
Oh, I see.
Yeah, so one runaway application in the staging namespace cannot physically starve the production namespace of compute or disk I/O.
That alone practically justifies the consolidation argument right there. But since we're talking about global organizations, we really have to look at georeplication.
Oh, yeah.
Because replicating data across continents is usually just a nightmare of third-party mirror makers and custom scripts.
Right, but Pulsar just handles it natively within the brokers, and the mechanics are highly tunable. You can do asynchronous replication, where a message is written to the local cluster, instantly acknowledged back to the producer, and then replicated across the world in the background.
So from the producer's perspective, the latency is essentially just the local network time.
Yes, but the trade-off is a brief window of eventual consistency. If that local data center suffers a catastrophic power failure before the background sync completes, you could have replication lag.
Right, but what if you're running, say, a financial ledger? You can't tolerate a single lost transaction, even if the primary data center gets hit by a meteor.
Well, then you utilize synchronous georeplication at the BookKeeper layer. When a producer writes a message, the local broker reaches out to bookies in multiple geographical regions.
Okay.
The write is only acknowledged back to the producer once a quorum of those remote data centers confirms they have the data secured on disk.
So you are paying the physics penalty of cross-country network latency for every single write.
You are. It will definitely be slower. But it provides absolute bulletproof consistency, and you can mix and match these strategies.
Oh, really?
Yeah, you can set up active mesh topologies where 3 data centers are all producing and consuming simultaneously, or edge aggregation patterns where dozens of small edge clusters sync asynchronously back to one central cloud cluster.
Okay, so we've established it can route anything, store anything, and sync it globally. But data at rest is just a cost center, right? To get value out of a stream, you have to compute on it.
Right.
And Pulsar functions are where this architecture starts to resemble a database replacement. We aren't just moving data anymore, we're processing it in transit.
It's serverless computing built directly into the brokers. You write a snippet of Java, Python, or Go, submit it to the cluster, and the brokers execute that code on the messages as they flow through the system.
That's wild.
Yeah, you don't need to export the data to Apache Flink or Apache Spark just for lightweight stream processing.
The documentation actually spends a lot of time on window functions, which I think is where the real power unlocks. Instead of evaluating one message at a time, you're evaluating a temporal subset of the stream. They break it down into tumbling windows and sliding windows.
Right, so mechanically, a tumbling window holds state for a fixed, non-overlapping interval. Let's say you configure it for 10 seconds.
Okay.
The broker buffers 10 seconds of messages in memory, executes your function across that entire batch, emits the result, flushes the buffer, and starts the next 10-second block.
So it's like batch processing, just in micro-intervals.
Exactly. But a sliding window is continuous. You define the window, say, 60 seconds of data, but you slide it forward every 1 second.
Oh, so it's constantly evaluating a trailing time frame.
Yes.
I mean, this is perfect for anomaly detection. Like, if you're looking for credit card fraud,
Yeah.
you don't want a rigid tumbling window because a fraudster might execute a transaction at second 9 of the first window and another at second 1 of the next window.
Right.
If you evaluate them separately, neither looks anomalous. But a sliding window acts like a heartbeat monitor. It constantly sees the density of those transactions as the time window rolls over them.
That's a perfect application for it. The function holds that sliding state in memory and computes the delta continuously.
But this brings up kind of the elephant in the room here, storage costs.
Ah, yes.
If we are using this as a system of record and BookKeeper is storing all these raw events on high-performance drives so the functions can access them fast, I mean, eventually you run out of disk space. Bookies are highly optimized, but they are expensive to run indefinitely.
Which is exactly why Pulsar built tiered storage directly into the architecture. It solves the exact problem of historical data retention without bankrupting your infrastructure budget.
I want to dig into how it does this without breaking the application layer. Because normally, if you archive data to Amazon S3 or Google Cloud Storage, the client application has to be completely rewritten to query S3 for historical data and the messaging platform for real-time data.
But Pulsar intercepts that complexity. Remember how BookKeeper uses Zookeeper to track ledger metadata?
Yeah.
When a ledger gets old, the tiered storage offloader copies the actual data segments to S3. But here is the critical part. It does not delete the metadata from Zookeeper. It just updates the pointer.
Oh, wow. So the consumer application just asks the broker for, message offset 100. The broker looks at the metadata, sees that ledger was offloaded, and seamlessly fetches the blocks from S3 and serves them back to the client.
The client has absolute zero awareness that the data was pulled from cold storage.
Yeah.
The read latency will be higher for that specific request, obviously. But the API interaction is completely identical. You can retain a practically infinite queryable backlog.
Okay, so on paper, this architecture sounds invincible. Independent compute, granular queuing, infinite storage. But theory is one thing. When you actually push this architecture to the breaking point on bare metal servers, you start finding bottlenecks that just don't exist on whiteboards.
Oh, absolutely.
Which brings us to that RCF paper from Brevo Systems.
Yes. This benchmark is just a masterclass in systems engineering.
Okay.
So Brevo handles physical security infrastructure like door sensors, access panels, meaning they process millions of mission-critical device events daily on Kubernetes.
Wow.
And they were seeing a problem. At moderate load, they were getting intermittent latency spikes of up to 213 milliseconds.
And in the physical security world, 213 milliseconds is definitely noticeable. I mean, if you swipe a badge at a turnstile, you don't want to break stride waiting for the server.
Right.
They needed predictable, ultra-low latency, so they stripped it down to bare metal machines to systematically hunt down the bottlenecks.
Yeah, and they identified 3 distinct mechanical choke points. The first was the Java runtime itself. Pulsar is written in Java, which relies on garbage collection to manage memory, and they were using the default G1GC algorithm.
Right, and G1GC is notorious because it occasionally has to perform those stop-the-world pauses to compact fragmented memory. The JVM literally halts all application threads to clean house.
Which was the direct cause of their 200-plus millisecond latency spikes. So the fix was moving to the newer ZGC generational algorithm. ZGC performs all of its expensive compaction work concurrently alongside the application threads.
So no more stop-the-world pauses.
None. The 99th percentile latency instantly dropped from a wildly erratic 197 milliseconds to a rock-solid 14 to 18 milliseconds.
That's incredible. Okay, so they fixed the software runtime, but even if the code executes perfectly, you're still bound by the physics of the physical disks, right? Which I think was their second bottleneck.
Exactly. Let's look at BookKeeper's write path. Before a bookie acknowledges a write, it has to physically sync that message to a journal on the disk. They were using older, worn SSDs.
And flash memory degrades over time, right? The write amplification makes syncing slower and slower.
Yeah. Their journal syncs were taking 5.1 milliseconds. That's an eternity for a high-performance system. It accounted for almost a third of their total delay.
So they threw hardware at the problem. They bought small, dedicated NVMe drives, which plug directly into the PCIe bus for extreme bandwidth, and isolated the journal writes exclusively to those drives.
And the impact was immediate. The sync time dropped by 99%, from 5.1 milliseconds down to 0.02 milliseconds. The paper explicitly notes that isolating the BookKeeper journal on an NVMe drive is the highest impact hardware investment you can make for Pulsar.
But here is where the detective work gets really incredible to me. They fixed the JVM, they isolated the I/O on NVMe drives, but they still found a third bottleneck. And this one was hiding deep inside the Linux kernel.
This is a phenomenal example of how the operating system can sabotage the application layer.
Right.
Even with separate drives, Linux groups I/O operations in the underlying block layer using the page cache.
Right.
When BookKeeper writes data, it doesn't immediately flush it to disk. It writes it to memory, the page cache, and marks those pages as dirty.
And the Linux kernel is designed to hoard those dirty pages to optimize write efficiency, right? It wants to batch them up.
Exactly. There's a kernel parameter called vm.dirty ratio, which is usually set around 20 to 40%. That means Linux will allow up to 40% of your total system RAM to fill up with dirty pages before it forces a background flush to the disk.
Wait, on a modern bare metal server with hundreds of gigabytes of RAM, 40% is an enormous amount of data.
It's tens of gigabytes.
Yeah.
So what was happening was BookKeeper would trigger a massive background data compaction, generating gigabytes of dirty pages. Linux would hoard them, hit that 40% threshold, and then just panic.
No.
Yeah, it would trigger a massive synchronous kernel write-back, totally saturating the storage bus and choking the entire system. Performance degraded to 22 milliseconds.
So how did they stop the kernel from hoarding?
They dropped the VM dirty ratio from 40 all the way down to 2.
Dropping it to 2%. So instead of batching massive gigabyte payloads, the kernel is forced to constantly trickle those dirty pages to the NVMe drives in tiny microflushes.
Exactly. It completely prevents the massive I/O bursts. The write pipeline stayed fluid, the bus never saturated, and the latency completely flattened out.
So just to recap the final state here, ZGC for concurrent garbage collection, isolated NVMe drives for the journal, and a 2% dirty ratio to bypass the Linux kernel hoarding. When they fired up the benchmark on that tuned configuration,
3 bare metal machines processed 1,499,947 messages per second.
with a median latency of 3.88 milliseconds and 0 failures.
The most staggering part of their scaling notes is that the physical CPUs were only at about 70% utilization. The machines weren't even maxed out. The only reason they didn't hit 3 million messages a second was because they physically saturated the 10 gigabit network cables.
So to double throughput, they don't even buy more servers. They just plug in 25 gigabit network cards.
And because of the stateless broker architecture we discussed earlier, if they expand this cluster to 15 nodes using key-shared partitioning, the scaling is perfectly linear. They project hitting 15 million messages a second, which is 1.3 trillion messages a day.
That level of performance fundamentally changes how you design applications. Like if we look at the IBM source, the immediate use case for this is consolidation. Tool sprawl is just an engineering plague right now.
Oh, absolutely.
If you are paying for the infrastructure, the enterprise support, and the engineering hours to maintain Kafka for streaming and RabbitMQ for queuing, I mean, Pulsar allows you to rip both out and replace them with a unified fabric.
It's also the ideal nervous system for microservices. Modern architectures rely on dozens of independent services firing indirect API calls at each other constantly.
Right.
When you have a sudden traffic spike, Synchronous HTTP calls timeout and fail.
Mm.
Pulsar absorbs that massive influx, queues it perfectly, and delivers it to the microservices at the exact rate they can handle it.
And obviously, anything mission critical. If you're processing financial transactions, the synchronous geo-replication ensures a ledger update is never, ever lost.
It provides the consistency of a traditional database,
Mm.
the horizontal scalability of a distributed stream.
Which brings us back to the premise we started with today. Think about the mechanical reality of what we just unpacked.
Okay.
If Pulsar can store events indefinitely in tiered storage on S3 without breaking the read path, and BookKeeper guarantees the safety and ordering of those events globally, and Pulsar functions can natively aggregate and compute that data in real time as a sliding window.
You have to ask why you are exporting your data out of the stream at all.
Exactly. We are so conditioned to think of event streams as just the plumbing that moves data from the app into a relational database like PostgreSQL.
Right.
But if the stream itself is permanent, instantly queryable, mathematically consistent, and programmable, why do we even need the database? I mean, why maintain a separate expensive plate for dessert when the infrastructure buffet can just synthesize it perfectly right in front of you?
It forces a complete reevaluation of what a system of record actually is.
It really does. It's a massive paradigm shift, something
Yeah.
for you all to chew on as you evaluate your own infrastructure and scaling bottlenecks. Until next time.